Hi, my name is Ben Owens. In this video, we're going to look at an overview of hypothesis testing and several examples. Hypothesis tests are a way for scientists and researchers to determine whether there has been some significant change in a quantity. To show the motivation for hypothesis tests, we're going to look at a scenario and compare three different cases. Suppose that we own a website and we decide to change the marketing strategy because we want to improve the amount of traffic that we get. We know that from previous months, on average, the website gets around 17,000 hits per day with a standard deviation of 1,500. Now, suppose that after the marketing strategy, we see these three different cases. In case one, suppose that after 3 weeks, we see that the average of those 3 weeks, the amount of hits per day is 5,400. That is, the sample of the 3-week average is 54,000. In this case, would there have been a significant change in the amount of traffic? Well, obviously the answer is yes, right? Because the sample average is so much higher than the original average. Now let's look at another case. Suppose that after 3 weeks, we took the sample average and it ended up being 17,021. Would you say that there was a significant change in the amount of traffic here? Well, not really. Although 1721 is higher, it's just not that much higher. That is, there's not really a significant change in the average. This third case is a little more difficult. Suppose that we found the sample average of 3 weeks to be 17,650. Now the question is, was there a significant change now in the amount of traffic? That is, did our marketing strategy work? That's what we're trying to figure out. Here it's a little bit harder to say. I mean, obviously the sample after 3 weeks is higher, but the question is this a significant change? In order to answer this question, we use hypothesis tests. So let's look at what was happening with this company before the new marketing campaign. We had the average of 17,000, the standard deviation of 1,500. Now, with a standard deviation of 1,500, we do expect that lots of days are going to be quite a bit higher than 1,700, and that lots of days are going to be lower than 1,700. And they'll average out to get 17,000. I mean, I keep saying 1,700. But on average, they'll come out to be 17,000. Since our new average, this X bar, this sample average, was only taking into consideration 3 weeks worth of traffic, maybe the average really hasn't changed. To look at this fact, here is 50 random numbers who have an average of 17,000 and a standard deviation of around 1,500. The question that we have to look at is, if we saw a sample average that was higher, that is, if what we saw from our sample was higher, did the actual average, did this mu really change? Or did we just happen to get a sample that was, with bigger numbers? Like suppose that we pulled a sample from this and it was these numbers here on the left. Here, they're all just a little bit higher than 17,000. And so if we made that sample, or if we picked a sample there, it would give us a sample average that was also higher. To look at another example of this, the problem with sampling is this. We don't exactly know what our sample is going to look like. Or better put, we don't know that our sample is actually going to be representative of the entire population. Look at this example, right? We have these 6 individuals, and say that they were the population, and we were going to choose 2 people from here as a sample to represent that population. Now, in this case, if we chose Connor and Andy, they have an average of 12, right? But that number does not represent the population at large. Since Connor and Andy are sort of on the higher end of these numbers, their sample average is going to be higher than the actual average. In this case, the actual average is 6.33. So we see that this sample that we choose can be a little bit high, right? What the kicker is that the probability of choosing that sample is only about 1 in 15, or 0.06, which is 6%. So although we can choose a bad sample, it's just not very likely that we do that. And this is what's going to actually allow us to use hypothesis testing, or this is sort of the engine that drives hypothesis testing. In our example, we want to look at these two possible scenarios. Now, we got a sample average of 17,650, right? That's what we got after 21 days. But there's two ways that might have happened. It may have been that the actual average has actually increased. And so now the actual average is bigger than 17,650. But it could also be that we just chose a bad sample, and that sample just happened to have higher numbers, and that it was just kind of a bad sample, which gave us a higher sample average. Both of these scenarios could be true, and honestly, we have no real way of knowing. What we can do, however, is talk about the likelihood of these scenarios. So to help us determine whether a change is significant, or to measure how significant a change is, we use hypothesis testing. And this is how it works. We start out with what we know, which is our old average was 17,000, and our sample average of 21 days was 17,650. What we want to do is figure out what the new average is, like the actual new average, not the old average, but now after the marketing campaign, what is our new average? The question is, where exactly does this new average, which we're going to call mu, where does it need to go? Is it down there kind of next to the old average? Is it kind of higher? Or is it somewhere maybe in the middle? This is what we want to try and figure out. So we set up two scenarios. The first scenario is this. We say, or we assume, that the actual average is just still the same as the old average. That is, that the new average after the campaign is still the same as the old one. That is, the marketing campaign actually didn't have any effect. It didn't change the average. It's still the same as it was before. We call this scenario the null hypothesis, and we denote that with H sub 0, or H naught. In this case, we would say that H naught is that mu is equal to 17,000, and that the average just has not changed from before. This would be what we call the null hypothesis. The second scenario is that our actual average is somewhere above 17,000. That is, that it's somewhere in this region above the old average. Now, unfortunately, we don't know exactly where it is, but we know that it's increased. So we call this scenario the alternative hypothesis, and we denote that as H1. Here we would write it as H1 is that the actual average is somewhere greater than 17,000. Notice that we don't specify where it is, but just that it's increased. So we want to compare these two scenarios. So this is what we know. In the first scenario, the one where we're assuming that the average hasn't changed, then we know that the average is exactly equal to 17,000. In scenario 2, the alternative hypothesis, unfortunately, the only thing that we can say is that mu is above 17,000. Like, we actually don't know exactly where this number is. We also know that from before, the standard deviation was 1,500. If we assume that the actual average hasn't changed, then we can assume that the standard deviation hasn't changed either. In the second scenario, once again, we're sort of left without knowing exactly where or what that ought to be. In both cases, we can say that the sample average, which we actually found, was 17,650. Because we know so much more information about the first scenario, that is the null hypothesis, that's what we're going to work with. In other words, we can't really touch the alternative hypothesis because we simply don't have enough information about it. But we can say things about the null hypothesis. So this is what we do. We test the null hypothesis, and it's what we call we find a test statistic. The question that we want to answer is this. If the average is 17,000, which is what the null hypothesis states, with a standard deviation of 1,500, what is the likelihood of getting a 3-week sample average that is 17,650 or perhaps even above that? That is, what is the likelihood of seeing what we actually saw under the assumption that nothing actually changed? Well, you might notice that this is a question involving the sampling distribution. That is, we're actually trying to figure out what our sample distribution would look like. So how we set this up is this. In 3 weeks, we have 21 days worth of data. So the size of our sample is 21. Since the original data set was assumed to be normal, then we can assume that the sampling distribution is approximately normal with these parameters. The average of our sampling distribution is the same as our average, which was 17,000, and the standard deviation of that sampling distribution is the standard deviation divided by the square root of n. That is divided by the size of the sample, which is around 312.77. We want to test what we actually saw. That is what we got when we did our test. This sample average, we want to find the z-score for that. So the z-score is simply 17,650 minus 17,000 divided by 312.77, which gives us a z-score of 2.07. This is what we call our test statistic, or the z-score for this null hypothesis. So if our z-score is 2.07, we can find something else that we call the p-value, which is the likelihood of seeing what we saw or something more extreme. That is, if we find the probability of getting 2.07 or higher, then that probability is 0.0192. This can be done, of course, by looking at the normal distribution table and finding the area above 2.07. This is what we call the p-value of our observation. Okay, so what does this mean? We have these two numbers, the z-score and the p-value. What does that tell us about our null hypothesis? Well, basically it says this. If the average is still 17,000, that was the null hypothesis, we're assuming that the average has not changed, then the probability of getting a sample like the one we saw is 0.0192. In other words, it's less than a 2% chance of getting what we saw from our sample. So what should we do? In this case, since we have such a low probability, we say that we should reject the null hypothesis. In other words, we made an assumption about where the average was, but our sample said that we got some sort of ridiculous result or some result that had a very low probability. Because of that, that is, because the z-value was big or the p-value was small, we reject the null hypothesis. So what we have shown is that there is statistical evidence from our sample that the average is not 17,000, which means that the average is probably somewhere above 17,000. And so we can accept the alternative hypothesis. This is the result that you might get from a hypothesis test. So here is another example. Suppose you flip a coin 150 times and you notice that the coin lands head 84 times. Is there statistical evidence to show that the coin is improperly weighted, or is this some sort of biased or loaded coin, right? Well, if the coin is fair, then what do we expect, right? If you flip a coin 150 times, we should get about half of those 150 to be heads, right? So we expect about 75 heads or a percentage of 50% heads. This is what we have as our null hypothesis. In other words, if we're trying to prove that the coin is loaded, then we assume for our null hypothesis that the coin is not loaded, or the coin is not improperly weighted. So the null hypothesis here would be that the proportion or the percentage or the probability of getting heads is 0.5. And the alternative hypothesis is that the coin is not equal to 0.5, or the coin is not okay. The proportion of times you get heads is not equal to 0.5. Now, in this example, the null or the alternative hypothesis is a little bit different than the one before. Remember, before we were trying to prove that the average was above a certain number. Here, we're simply trying to prove that it's not equal to that. What that means is we're going to use what's called a two-tailed test. Instead of just trying to prove that it's bigger, we're actually going to prove that it's either bigger, or try to prove that it's bigger or smaller. So we call this a two-tailed test. Now we can test this null. In this case, we're going to test the null hypothesis, which is that the proportion was 50%, or that p was 0.5. The sampling distribution for this proportion gives us this. The average of the proportion is just going to be 0.5. The standard deviation is given by the square root of p times 1 minus p over n, which is 0.0408. And the number that we're going to test, what we actually saw, our observation, is that we saw 84 heads out of 150, which gives us the proportion of 0.56. So in this case, our test statistic is given by finding the z-score, which is 0.56 minus 0.05 over 0.0408. Therefore, the z-score is 1.47. And since this is a two-tailed test, we have to find the probability of just being above or below 1.47 standard deviations away from the average. That is, we have to actually take the probability of having something higher than 0.56 or lower than 0.44, and that probability is found by adding those two regions in the normal distribution. So in this case, our p-value is 0.1416. So what does this mean? So our z-value in this case is a lot smaller than the one before, and the p-value is a lot bigger. Now the interpretation says that in this case, we have about a 14% chance of seeing what we saw, that is, looking, finding, flipping a coin that's off by at least 6%. Well, that's going to happen 14% of the time, even if the coin is not weighted improperly. In other words, remember, since this was the null hypothesis, our assumption was that the coin was fair. So even with a fair coin, we have a 14% chance of seeing what we actually saw. So what should we do? Well, unfortunately, our statistical evidence this time isn't really strong enough to reject the null hypothesis. So we shouldn't reject the null based on this observation. In order to reject the null, our z-value must be big and our p-value must be small, and that simply wasn't the case here. So in this example, we can't reject the null hypothesis because there wasn't enough statistical evidence. So we can accept the null hypothesis, right? Well, not quite. Failing to reject the null only implies that our evidence wasn't strong enough to see significant results. It doesn't mean that the null hypothesis was true or that the null hypothesis was correct. So when you're doing a hypothesis test, there's really one of two outcomes. You can either reject the null and accept the alternative, or you can just have inconclusive results. Doing this type of testing never really guarantees that the null hypothesis is true. It simply can sort of prove, or at least statistically show, that it's more than likely false. So how did we choose this z-value? In other words, in the first question, our z-value was around 2 point something. In the second example, the z-value was less. It was 1 point something. How big does this z-value need to be in order to show a significant change? Or another way of asking is, how small does the p-value need to be in order to show a significant change, or in order to reject the null? Well, the answer is it depends. It depends on the type of scenario that we're dealing with. For instance, suppose that you have some sort of public opinion poll for a beauty magazine where you're trying to see people's opinions on different lipsticks and if those opinions have changed. For this type of hypothesis test, there would be no reason to have a high level of significance. That is, your z-value and your p-value don't have to be too strong. However, suppose that we had medical testing on a new drug to determine its fatal dose. How much can you take before it kills you? In this case, the stakes are very high, and so we would want a much higher level of significance. Because we have these differing types of situations, when we do hypothesis testing, we actually first choose the level of significance that we want. We call this significance level alpha, and this is actually the cutoff point that we use for our p-value. The usual suspects are alpha being 0.1, or alpha being 0.05, or alpha being 0.01. We can choose any value we want for alpha, but these are usually the ones that people use. If the p-value for a hypothesis test is less than alpha, that means that we can reject the null and accept the alternative. Otherwise, our results are inconclusive. So, if the stakes are high, we want alpha to be very small because we don't want to make a mistake, or we want a higher level of significance. So, the higher the stakes, the lower we want alpha to be, which implies the higher the z-score is going to need to be. Here is a table that gives us the critical values, we call them, for these different levels of significance. If we have a right-tailed test, that is, if the thing that we're testing is like the example 1 that we saw, where we're testing that something is bigger than what it was before, then the z-value for alpha is equal to 0.1 is 1.28. If the alpha is equal to, if the level of significance is the 0.05 level, then the z-value is 1.645. Notice as the level of significance, as the alpha value decreases, this z-value increases. Like, this is kind of our cutoff point for our z-scores. That is to say, at this higher level of significance, alpha is equal to 0.001, in order to reject the null, here we have to get a z-score of 3.09 or higher. The pictures here demonstrate the areas that these p-values are representing. This is sometimes called the rejection region. That is the region down here. And as you can see, as the level of significance increases, this rejection region becomes further and further away from the average, or smaller and smaller. For a two-tailed test, notice that the rejection region is on both sides, that is higher and lower than the average. In this case, our z-score, or we get a significant test if the z-value is higher or lower than the critical values there. So let's look at a third example. In this case, we're going to sort of write out the steps that we typically take when doing a hypothesis test. In this, according to a 2009 census data, on average, the drive time to work was 25.1 minutes. Suppose in 2013 a researcher wanted to prove that the drive time has increased. So they sample 19 individuals, and they see that the sample average there was 26.9, and the standard deviation of that sample was 4.3. At a significance level of alpha is equal to 0.05, can the researcher claim that there has been a significant increase? Now, in this case, notice that right off the bat, we set our level of significance at 0.05. This is typically how it's done, is that you decide what your level of significance is going to be before performing the test. Now, notice that here our sample size is pretty small. That is, they only tested 19 individuals. In this case, that means that instead of using the z distribution, we should instead use the t distribution. The reason for that is because of that small sample size. The process that we're going to use is exactly the same, except that when we look for the critical values, we're going to pull them from the t distribution instead of the z distribution. So let's perform this hypothesis test. The first step is to state the null and alternative hypothesis. In this case, the null hypothesis would be that the drive time has not changed, or that mu is still equal to 25.1. The alternative hypothesis is that the drive time has increased, or that mu is greater than 25.1. That means we're going to have a right-tailed test. It's going to just be looking at the area to the right, because it's greater than. Step 2 is to find the critical values based on the level of significance. Now, since alpha is equal to 0.05 in this case, we are going to use the t distribution with 18 degrees of freedom. Remember that when you have your sample size, the degrees of freedom is one less than that sample size. So since there was a sample of 19, our degrees of freedom are 18. So we can find the critical number by looking at the t distribution table in the column for 0.05 and then in the row for 18. In this case, we get the number 1.734. This is our critical value, or this is the number that if we surpass this, then we can reject the null. Step 3 is that we compute the test statistic. In this case, we take our average that we got from our sample, 26.9, subtract the original average, and divide by the sample standard deviation over the square root of 19, which is the size of the sample. When we do that, we get 1.82. So what does that mean? Since the test statistic, 1.82, was greater than the critical value, that tells us that we can reject the null and accept the alternative hypothesis. And that means that based on our statistical evidence, it looks like what? That the drive time has increased. That is, the alternative hypothesis was that the average was higher than 25.1. And so that means that we have statistical evidence to show that the drive time has increased. We might say it like this. Based on the sample at a significance level of 0.05, the researcher has enough evidence to claim that the average has risen. So here is what hypothesis testing is all about. This is how it works. Hypothesis tests are useful for determining whether a change has occurred in a parameter based on a sample that is taken. In order to be able to use probability, we have to use the known quantities which come from the null hypothesis. The alternative hypothesis is typically what we're trying to prove. If the statistical evidence is strong enough from our sample, we can reject the null and accept the alternative. If not, the results are inconclusive. If we still want to prove our result, then we might consider taking a larger sample. Now, this is quite a process. Hypothesis testing is kind of a lot to wrap your mind around, but luckily it follows the same 4 steps each time. I hope this video has been helpful in helping you see how hypothesis tests work and why they work the way they do. Thanks for watching.